Okay, everybody, we're going to complete the next part of Module 5, which is going to be talking about combustion analysis, which typically students seem to struggle with, at least initially. So I'm going to in a very detailed manner, walk through the theory as well as how you do these different problems, and hopefully that will help you understand the idea of using combustion analysis to determine empirical and molecular formulas. So let me go ahead and start sharing. Okay. Combustion analysis is a common technique for analyzing compounds. Basically, you take the compound and you burn a known mass of that compound, and then you can weigh the amounts of products. This is used generally for organic compounds that contain carbon, hydrogen, and oxygen. And you use regular combustion and oxygen in order to do this reaction. By knowing the mass of the products and the composition of constituent elements in the product, the original amount of the constituent element of that original sample can be determined. Remember, in a combustion reaction, a hydrocarbon or a hydrocarbon containing oxygen will react with oxygen to form carbon dioxide and water. All of the original carbon in that original sample forms carbon dioxide. All of the original hydrogen in the original sample forms H2O, water. I can determine carbon and hydrogen from the amounts of carbon dioxide and water that form in the combustion analysis. I cannot determine directly the original mass of oxygen in the sample. I need to go through a somewhat complicated analysis and figure out by subtraction the mass of oxygen that was originally in the sample. And I'm going to show you that in detail as we go over the problems. Once the masses of all the constituent elements in the original compound have been determined, the empirical formula can be found in very similar manner to what we just discussed before with the percent composition. So during combustion analysis, a compound of unknown composition is burned with oxygen to produce the combustion products carbon dioxide and water. Those two products are separated, and their amounts, the amounts of those products that are produced, are determined by an automated instrument. What we really need to focus on is that my hydrocarbon, which contains carbon and hydrogen, all of the carbon is responsible for the amount of carbon dioxide that forms. And all of the hydrogen from that original hydrocarbon sample is responsible for the amount of water that is formed. Oxygen has to be done separately. It can't be determined directly from the amount of carbon dioxide and water that is yielded in a combustion analysis reaction. Here's an example. I have a 1.50 gram sample of hydrocarbon. It undergoes complete combustion to produce 4.40 grams of carbon dioxide and 2.70 grams of water. Here, I'm looking for the empirical formula. This type of problem is done in the following way. I'm going to look at 4.40 grams of carbon dioxide. That means that whatever amount of carbon in that hydrocarbon sample that was used to do this combustion produced this specific amount of carbon dioxide. And I know my total sample, this is my total sample mass. Sometimes I need this and sometimes I don't. Be wary of problems that give you information that you don't need. Many times in problems, they will give you information that you don't need to see if you can recognize the fact that you don't need that information in order to solve the problem. Well, let's start with this one. So the first thing I'm going to do is convert the amount of carbon dioxide to moles of carbon dioxide. So for every 1 mole of carbon dioxide, I have 44.01 grams of CO2. Let me just check that number. Carbon dioxide has 12.011 plus 2 times 16. Yeah, I get 44.01 grams of carbon dioxide. This would be the molar mass of carbon dioxide. Now, remember before, 1 mole of CO2 is equal to 1 mole of carbon and 1 mole of O, and 2 moles of O. That's the molar ratio. The formula gives me the molar ratio. So I can do this next conversion. For every 1 mole of CO2, I have 1 mole of carbon because of this formula, because of this relationship up here that I can get from that formula. So this allows me to determine the amount of carbon, the moles of carbon that was in my 1.50 gram sample. And remember, my empirical formula is a ratio of moles of constituent elements. So I have 4.40 divided by 44.01. That's going to give me 0.09998 moles of carbon. Now, let's look at the other amount of product that we got. We also got 2.70 grams of water. And just like I could do this relationship, I also have this relationship. For every 1 mole of H2O, I have 2 moles of hydrogen and 1 mole of oxygen. That's another relationship that I can get from that formula. So let's look at this. Let's convert the grams of water to moles of water. So for every 1 mole of H2O, I have 18.02 grams of H2O. That's the molar mass. If I take 16 plus 2 times 1.01 grams, I get that value as my molar mass. Here's the thing. For every 1 mole of the molecule, I have 2 moles of hydrogen. That's really critical, this 2, because this is that ratio in the formula. So when I do this, I can calculate the moles of hydrogen that were in the original sample. So I have 2.70 times 2 divided by 18.02. And this gives me 0.299667 moles of hydrogen. Now I do the exact same thing as I did before. I'm going to look at the ratios. I'm going to divide by the lowest number of moles. So what I'm going to get is I divide this by 0.09998. I get 1. I divide this by 0.09998. And what I'm going to get here is 2.99 or 3. So here's my empirical formula. My empirical formula is carbon H3. So this is the empirical formula of this compound. And that is my final answer to this problem. I didn't need that sheet. Okay. Let's do another one. That one only had carbon and hydrogen. So I could solve for the moles of carbon and the moles of hydrogen directly. This one has carbon, hydrogen, and oxygen. So this is going to require a little bit more thought because I have to get this indirectly. I cannot use the CO2 values or the amount of CO2 or the amount of water to calculate oxygen. Don't try to do that because you will be horribly wrong. All right, this is the total amount of sample that contains all of these compounds. This amount, this is the total amount of my unknown sample that I combusted. And that amount gave me 0.3664 of CO2 and 0.1500 grams of water. Again, I'm looking for the empirical formula. Okay, so let's do this. I'm going to start with the same procedure that I used before. I'm going to take 0.3664 grams of CO2. I'm going to convert to moles. And then I'm going to use the formula as a conversion factor. For every 1 mole CO2, I have 1 mole of carbon. And I'm going to do that math. And what I'm going to get is 0.3664 divided by 44.02. And that gives me 0.0083235 moles of carbon. I could also write that in scientific notation. That's where I'm getting to the point where I could write that as 8.32 times 10 to the minus third. Doesn't matter at the moment. Let's look at hydrogen. If I have 0.1500 grams of H2O, I'm going to do the same thing I did before. For every 1 mole H2O, I have 18.02 grams H2O, which is the molar mass of water. And then remember, for every 1 mole of H2O, I have 2 moles of hydrogen, elemental hydrogen, or hydrogen atoms. So make sure you understand that this 2 is critical to the success of calculating the amount of hydrogen. If I calculate that, then I'm going to get 0.1500 times 2 divided by 18.02, and that gives me 0.01668 moles of hydrogen. That's the only information I can get from this data regarding the elements that were composed in the original sample. I cannot directly get the amount of oxygen, sorry. So what I have to do is I have to calculate the amount of hydrogen, or the amount of oxygen that was present in the sample, the grams of oxygen that was present in the sample by using this data. I know that this 0.2500 gram sample contains 0.00832335 moles of carbon and 0.016648 moles of hydrogen. So what I can do is calculate the grams in that amount of carbon moles. So for every 1 mole carbon, I have 12.011 grams carbon. So if I look at the amount of carbon in that mole value, right, I'm going to take that moles of carbon and find out the gram amount. So this is 0.09997 grams of carbon. This is the amount of carbon that was present in that 0.2500 gram sample. I'm also going to do this for hydrogen. For every 1 mole of hydrogen, I have 1.008 grams of hydrogen. So that's going to give me 0.01678 grams of hydrogen. Okay, so that means something. This is the amount of carbon that was present in the original sample in grams. This is the amount of hydrogen that was present in the original sample. So if I take the total mass of the sample, 0.2550 grams total, and I subtract 0.09997 grams of carbon, and I subtract 0.0167 grams of hydrogen, what that gives me is the grams of oxygen present in that original sample. So I'm going to go 0.2550 minus the amount of carbon, and then I'm going to subtract from that the amount of the amount of hydrogen. And what I get is I have 0.1382 grams of oxygen that was present in the original sample. Now, I can use this information and figure out the moles of oxygen that were in the original sample. So if I have 0.1382 grams of oxygen, and then I have 1 mole of O, and each mole of oxygen atom is 16.0 grams of oxygen, that means I have 0.008640 moles of oxygen in that original sample. So now here is the moles of carbon. Here are the moles of hydrogen, and here are the moles of oxygen. That's what I'm going to take a ratio of to find the empirical formula. So remember, I'm going to divide by the lowest number which is going to be this guy. So I'm going to divide by 0.00832335. That's going to give me 1. If I divide this 0.00832335, what I'm going to get when I do that, I'm going to go up on my calculator a little bit. So 0.016648, oops, 0.016648 divided by 0.00832335, and that's going to give me 2.00. So that's fine. And then this divided by 0.00832335 is actually going to give me notice they're not exactly the same, but this will give me 1.03, so it's well within my 0.1 away from the whole number. So this is also 1. So my empirical formula here is carbon 1. I don't have to indicate the 1 in those subscripts. Hydrogen 2, oxygen 1. And this is the empirical formula for this problem. So this is the answer for this problem. Remember, if I had the molar mass, I would be able to figure out how what the molecular formula is as well. But remember, the key to this part is I have to figure out how much oxygen is present in my original sample in order to do this problem. Okay. All right. Let's do another one. Quinone, which is used in the dye industry and photography as an organic compound containing only carbon, hydrogen, and oxygen. What is the empirical formula of the compound if you find that 0.105 grams of the compound gives 0.257 grams of CO2 and 0.0350 grams of H2O? All right. Given a molecular weight of approximately 108 grams per mole, what is the molecular formula? So first, I need to find the empirical formula, and then I need to find the molecular formula because I have the molar mass. So let's go ahead and do this the same way that we did it before. This is the total weight of the compound. And then I have this amount of carbon dioxide that was formed from combustion of that amount. So 0.105 grams of the compound produce 0.257 grams of CO2 and 0.0350 grams of H2O. So I'm going to take 0.257 grams of CO2 and find the moles of carbon. For every 1 mole of CO2, I have 44.02 grams of CO2. I know from the subscripts for every 1 mole of CO2, I have 1 mole of carbon. So if I do this math, I have 0.257 divided by 44.02, and I get 0.005838 moles of carbon. Let's do the same thing with the other quantity produced, which is 0.0350 grams of H2O. We're going to find the moles of hydrogen. 1 mole of H2O, I have 44.02 grams. Oops, I'm just like not thinking. 18.02 grams of H2O, that's the molar mass. And then remember that 2. For every 1 mole of H2O, I have 2 moles of hydrogen. And again, remember that 2. That's really important. So this gives me 0.0350 times 2 divided by 18.02. I get 0.0038846 moles of hydrogen. Again, I'm done with the combustion data at this point because I cannot directly use the amount of carbon dioxide or the amount of water to figure out the amount of hydrogen or oxygen that is present in my original sample. So I'm going to do the same thing I did in the last problem. What I'm going to do is figure out how many grams of carbon are in this original sample of material. So I'm going to use 12.011 grams of carbon for every 1 mole of carbon. And that means if I do that in my calculator, I have 0.07012 grams of carbon in my original sample. Let's figure out the amount of hydrogen. I have 1.008 grams of hydrogen for every 1 mole of hydrogen. And if I do that, I get 0.0039156 grams of hydrogen. Those are the amounts that were present in this 0.10150. Since the compound only contains carbon, hydrogen, and oxygen, what I'm going to do is find the oxygen by difference. So I have 0.105 grams total sample minus 0.07012 grams of carbon. That's the amount of carbon that was present in that sample, minus 0.0033952, 3915 actually, 15. Grams of hydrogen. If I do this math, 0.105 minus the amount of carbon minus the amount of hydrogen, and what I find out is that what's left over is 0.030961 grams of oxygen. So this is the amount of oxygen that was present in my original sample. So now I can go back to what I was doing before. I have 0.0309661 grams oxygen. I'm going to calculate the moles. For every 1 mole oxygen, I have 16.00 grams oxygen. And what I'm going to get is 0.0019351 moles of oxygen. So now, this is the mole of carbon in the original sample. This is the moles of hydrogen in the regular sample. This is the moles of oxygen in the regular sample. Which one is the lowest number? Because that's what I'm going to divide by. So that's the lowest number. So what I'm going to do is divide by 0.0019351. That'll give me a 1. If I do this, 0.01193, watch your zeros. I almost dropped a 0 here. What I have is 0.0019351. So what I calculated was 0.00388846 divided by 0.0, wait a second, divided by 0.00, why is my calculator going nuts? All right, let me put this back in there. 0.00388846 divided by 0.0019351, and this gives me a 2. It's 2.007. And then when I divide this, 0.005838 divided by 0.0019351. That gives me 3. So my empirical formula is carbon 3, hydrogen 2, oxygen. When I write my empirical formulas for these hydrocarbons, I always write them in the order carbon, hydrogen, oxygen. Right? Carbon comes first, then hydrogen, then my heteroatoms, which are atoms other than carbon and hydrogen. So that's part 1. I just determined the empirical formula of the compound. Now I need to know the molecular formula because I have the molar mass. So I know that I have to calculate N. So N is going to be the molar mass divided by the mass of the empirical formula. So our mass was 108 grams per mole. Now, if I calculate the molar mass of that, I have 3 times 12.011 plus 2 times 1.008 plus 16.00, and I end up with 54.0 grams per mole, which is the mass of that empirical formula fragment. So that goes down here, and you can see this integer value is 2. So my molecular formula is going to be 2 times the empirical formula, which is going to be 2 times C3H2O, which is going to be C6H4O2. So this is the molecular formula, and that answers the problem as asked. Now notice, this is a really, really steppy problem. And for full credit on an exam, you basically need to show everything that I did in order to get full credit. You can't do this stuff in your head. You have to write it out. So write it out, and you have to show me you understand it in order to get full credit on the exam. I think there's one more, and this next one is even more complicated than the other one, and we have to walk through this really carefully. So I have a sample and 40.10 grams of that sample. Now notice I have carbon, hydrogen, chlorine, and oxygen. I do combustion analysis on that sample. I get that much CO2 and this much H2O. Now notice I have another sample, and the sample of this mass is 75 grams. And this contains, that 75 grams is 22.06 grams of chlorine. All right, so that's a little twist here. So I want to find the empirical formula. So let's start with what we just did before. Here's my original sample that gave me the CO2 and the water data from combustion analysis. So we can find carbon, hydrogen, and oxygen from that data, just like we did before. So let's start doing that. If I have 58.57 grams CO2, for every 1 mole CO2, I have 44.02 grams CO2. And then using the formula, for every 1 mole CO2, I have 1 mole carbon. I do this, 58.57 divided by 44.02, and I end up with 1.3305 moles of carbon present in this 40.10 grams. Let's do water now. I have 14.98 grams of water. I have, for every 1 mole of H2O, I have 18.02 grams of H2O. And then remember from the formula, I have this 2. So I have 2 moles hydrogen for every 1 mole H2O. Do not forget this 2. That's what the formula is telling me. When I calculate this, I have 14.98 times 2 divided by 18.02. And I get 1.6626 moles of hydrogen. Well, I can find the amount of oxygen indirectly, except I also have chlorine. So I have to take a little segue here. I am going to figure out the percent of chlorine in my original sample. To do that, I know I have 22.06 grams of chlorine in my total sample that has 75.00 grams of total sample. I multiply that by 100, and what I find is that this sample is 29.41% chlorine. Now, that's valid for this amount and this amount because it's the same compound. So now I have a way to calculate the gram amount of carbon, hydrogen, and chlorine in my original 40.10 gram sample. And then I can take the difference and find out how much oxygen was present there. So I'm going to do the same thing that I've done before. I'm going to find out the mass of carbon in this 40 grams sample. For every 1 mole of C, I have 12.011 grams of C. So that is going to give me 0.1108 grams of carbon. Wait, that can't be right. Oh, I divided. All right. Brain fart. All right. I'm going to take 1.3305 times 12.011, and that's much better. I'm going to get 15.981 grams of carbon in that 40. Now, notice I caught myself because I ended up dividing instead of multiplying, and that number was just way too small. And that's how I figured out that that wasn't incorrect. And then I went, instead of going with it and knowing, oh my gosh, at the end, I did something major and I have to backtrack every step. I'm kind of going to check every step individually and see if it makes sense before I go on. Sometimes it'll work. Sometimes I do have to get the wrong answer and then backtrack and try to figure out where I went. Let's find the amount of hydrogen. For every 1 mole of hydrogen, I have 1.008 grams of hydrogen. So I end up with 1.6759 grams of hydrogen in that 40 gram sample. Now here's the part where I use this value. So my sample mass is 40.10 grams. And if I multiply that by the decimal form of my percentage, right? 40.10 times 0.2941, that tells me that 11.79 grams of chlorine are present in that 40 gram sample. So now I can figure out the mass of oxygen. If I have 40.10 grams total, I take away the carbon, I take away the hydrogen, and I subtract the chlorine. And what I'm going to get is 40.10 minus 15.981 minus 1.6759, and that gives me 22.4431 grams of oxygen in that sample. Now, one thing I want you to recall, let's see, I'll use green. This is the moles of carbon in the original sample. This is the moles of hydrogen in the original sample. I still need the moles of chlorine and the moles of oxygen before I can do my mole ratio and come up with that empirical formula. So I'm going to do 11.79 grams of chlorine, and I'm going to calculate the moles in that chlorine. For every 1 mole of Cl, I have 35.45 grams of CL. So that's going to give me 11.79 divided by 35.45, and I get 0.33258 moles of chlorine present in my 40-gram sample. Then I'm going to take the 22.4431 grams of oxygen, convert that into moles. For every 1 mole oxygen, I have 16.00 grams oxygen. So when I do that math, I'm going to get 22.1 divided by 16. I'm going to get 1.4030 moles of oxygen. Well, now I have the other 2 mole that I need in order to find the ratio. So out of all those numbers, the smallest one is going to be chlorine. So I am going to divide, what color haven't I used? I used gray. I'm going to divide everything by 0.33258. This is going to give me a 1. If I look at this, 0.33258, 1.3305 divided by 0.33258, that gives me 4. If I do this guy, 0.33258, I have 1.6626 divided by 0.33258, and that gives me a 5. And then I have this, which is 0.33258, and 1.4030 divided by 0.33258 is going to be let me make sure that doesn't make any sense. So let me check. I'm going to go up here. I'm going to say and I still get a 4.3. Actually, I get a 4.22. So did I make a mistake, or do I really have to multiply everything by 4? Because that would what I'd have to do here. I'm going to go check my oxygen numbers because I want to make sure that everything is correct. So I am going to look at 40 minus 15.981 minus 1.6759 minus 11.79. And now I get a different number. So let me check this again. This is what happens with these STEPI problems. If I have 40.10, I'm subtracting 15.981 grams of carbon and 1.6759 grams of hydrogen and 11.79 grams of chlorine. That's my problem. This is 10.6531. So I'm going to use 10.6531 here. And what I'm going to get is 0.6658 moles. So when I divide that, I'm going to get 2. All right, that makes more sense. I hope everyone can follow that. You definitely have to take your time, double check things when things don't seem like they're wrong. You want to go back and redo stuff. And what I get here is that my empirical formula is going to be carbon 4, hydrogen 5, oxygen 2, and then Cl1. And that is going to be the answer to this problem. So hopefully, as I go through and I solve my mistakes and reason through stuff, you'll be able to figure out how to do these problems. If you have any questions, as always, let me know. But that's the end of Module 5. And hopefully this all makes sense. These are the types of problems, these are the types of problems that you are responsible for knowing in terms of the test. Now, this took us a long time to solve. So you have to give yourself plenty of time for the homework, and you need to know this procedure pretty quickly because the tests are timed, and if you have to sit here and stumble around and look for how I'm going to do this procedure, this one problem, which might be worth 5 or 10 points, is going to be your test because you don't understand how to do the process. So my advice to you is to make sure you do these problems so that you know exactly how to do them so you can do them relatively quickly as you go through the tests when we come to them. Hopefully this makes sense. I will stop talking now. If you have any questions, make sure you reach out. All right, bye-bye.